Now, attribute is also called as rich metric. Rich metric. Now, this is not simple metric, it's rich metric. So we don't call BGP metric. See, if you talk about RIP, there is something called metric, hop count. If you talk about EIGRP, bandwidth and delay or the metric. OSPF, cost is the metric. But in BGP, we don't have any metric. We call as BGP attribute. BGP attributes. See, attributes are like plug and play metrics. Plug and play means what? Plug and play means what? Now, I have a cell phone, and I want to hear some music from my cell phone. What I do, I don't listen using a normal speaker in my cell phone. I just plug in my headset and I listen the music with a nice headset. By doing so, I'm not disturbing my neighbor. I can listen to the song me alone. So it's plug and play. I just plug in and then it plays for me. I need not to restart my cell phone because I added the new accessory. Likewise, you have laptop. You just plug in your pen drive. You can use the pen drive, and you eject it. It is ejected. It becomes out. So when you have pen drive in your laptop, you get additional GB, right? So let's say by default you have 500 GB in your laptop, and you are adding on 32 GB pen drive to your laptop. So what happens? Your storage is incremented 500 plus 32. So the efficiency of the laptop is getting incremented. Or let me give you another example. Now you have a desktop. This desktop has got 8 GB RAM. You want 16 GB RAM. What do? You just plug in another 8 GB RAM, and your desktop efficiency improved now. 16 GB RAM, more faster. Likewise, attributes can be plugged in anytime and plugged out anytime. As you plug in the pen drive to increase the memory, to increase the storage, and plug out the pen drive to decrease the storage. Likewise, you can plug in the metric whenever you want and take the metric out whenever you don't want. That's why we call it as plug and play. See, can you remove cost from the OSPF? Cost is the metric. If you cannot remove cost from OSPF, that is the metric in which OSPF determines the best path. Cost is part of OSPF. You cannot separate it. Likewise, hop count you cannot separate from RIP. Hop count is the metric of RIP. You cannot say I'll make cost as a metric for RIP. You cannot say that. You cannot say I'll remove hop count and put cost as a metric for RIP. Cannot do that. But in BGP it is not like that. There are 0 to 11 attributes. 0 to 11 attributes. Whenever you want any of those 0 to 11 attributes, totally 12 attributes. Whenever you want some attribute, you just plug into your BGP. Now BGP will obey according to what you have added. The attribute you add. According to the attribute, BGP will start behaving. Whenever you want something more, you add more attribute. Whenever you don't want an attribute, you want BGP to decide, take some other decision. According to that, you choose one attribute and plug it to BGP. So based on how you want BGP to behave, you can make BGP to behave. Based on your company policies, based on your company rules and regulations, these attributes can make BGP to work. OSPF will not work based on your company policy. OSPF will obey metric called cost. Only based on cost OSPF will work. Based on hop count, RIP will work. Based on bandwidth and delay, EIGRP will work. But here is a protocol which works based on what attribute you add. So what sort of attribute we will add? We will add attribute according to our company policy, according to our company rules. Whichever the attribute is suitable, we'll take those attribute and we will inject to BGP's path selection process. So BGP will decide path as per our rules and regulations, our policies. That's why it is called as rich metric. And that's the reason BGP is a very good protocol to work between autonomous system. When we have multiple autonomous system like this, we will have lot of rules and regulations, a lot of policies to talk to other autonomous system. Now this type of setup we call it as multi-homing, which setup one autonomous system is connecting to more than one autonomous system. See, router 1 is multi-homing. This is one home and this is another home. This is connected to multi-autonomous system. This we call it as multi-homing. Now this is how internet looks like. You know, this autonomous system is connected to another autonomous system that is connected to. This is how internet is very big. Now when some traffic from 2 wants to go to 3, it has to use this autonomous system 1. Without going through 1, it cannot reach 3. Now what happens? Traffic from 2 is using the bandwidth and device that is there in autonomous system 1 and reaches 3. Now will this guy be happy? His device is used, his bandwidth is used, but it is not his own traffic. So what this guy will do? He will have some agreement with this guy and this guy. According to the agreement, he will write some policies in path selection. So that policy can be implemented only through BGP's attribute. Will not allow someone to simply use its bandwidth and its device without having some agreement, without having some business related negotiation, meaning without taking some money. Autonomous system 1 will not really allow autonomous system 2 to use autonomous system 1's device and go there. So some sort of policy will be there and some sort of bandwidth sharing. Not all the bandwidth in this network will be allowed to use. So there will be some policies for the outside networks traffic, and there will be another policy for the inside network traffic. So those things are what? Those things are company policy. Now those policies can be considered by the routing protocol when we know how to tune the attributes. So attributes are the one which makes BGP really a special protocol here, different from the other protocols. This is unique. So such an attribute is what we are going to learn today. We are going to learn some attributes. Now first attribute is that zeroth attribute. The zeroth attribute is valid or reachable next hop. But this is not seen as an attribute in many documents. Valid next hop. This is one of the attribute, see, for designing which path to take. See, there are two paths for AS1, for autonomous system. One, to reach some network here, x dot y dot z dot 0 network. To reach this network, there are two different paths. One via autonomous system 2, the other one via autonomous system 3. Now, which path should I choose based on the attribute? First thing what it will see, this autonomous system will see whether the next hop for this XYZ is reachable via this way or this way. You remember in the previous class we saw you will have a next hop address, but if it is not a reachable next hop address, it will be just valid, not the best. If it is not the best, it cannot be used in the routing table. Now, if I have two routes to reach XYZ, XYZ is advertised to, let's say this is AS4, it is going to AS4 and AS4 is giving to AS2 and AS2 is giving to AS1. Likewise, XYZ is going to AS3 and AS3 is giving to AS1. So AS1 is learning it from two different sources. It learns XYZ from two sources. One is from autonomous system 2, the other one is from autonomous system 3. Which one I'll choose? So that decision is based on the attribute. So, valid next hop, reachable next hop. If one of the next hop is not reachable, it will choose the other next hop which is reachable. It will choose the best path. Let us say here in this router here you forgot to say next hop self, but here you have said next hop self, here you have not said. So router here in this autonomous system, though it is learning the route from two different sources 2 and 3, it will decide to go via 3. Why? For this router it has got a valid next hop address because you use next hop self command here. It has got a valid next hop address, so it will choose this path. Though I have two paths, I am using one path. And which one path? This one path. When going via router autonomous system 3 will be seen in the routing table. This route will not be seen in the routing table, but it will be there in the BGP table. It will be there in BGP table as valid but not best. That is one. Next one is attribute of number 1, weight. Weight is a Cisco proprietary attribute. Cisco's attribute, weight. Weightage. Let me draw the diagram neatly and explain you. Let's say this is one autonomous system called AS1 that is connected to the other autonomous system. This is connected to another autonomous system. So this is AS1, this is AS2, AS3, AS4, AS5. There are 5 autonomous systems. And this is router number 1, 2, 3, 4, 5, 6, 7, 8, 9. Right. Now, Let's say there is a network from here advertised, that is 9.9.9.9. So this will be given to AS3 and AS3 will give to AS1. Likewise, this will be given to AS6. AS6 will give to AS5, AS2. Sorry, AS4 will give to AS2. AS2 will give it to AS1. Now, router 3 and router 2, they are receiving the update from two different autonomous systems. Or AS1 is receiving the update of 9.9.9.9 from two different autonomous systems. One is via AS2, another one is via AS3. You know about one thing. What is that? EBGP's address will be carried when it is given to IBGP. So what we do is, to provide reachability, we say next hop self here, next hop self here. So R1 is learning route to reach 9.9.9.9 and both the routes are valid. Why? Both are giving a reachable address. R2 is putting its own address and giving. R3 is putting its own address and giving to R1. Because we use next hop self command, it happens. So we got a valid next hop. Because there is a valid next hop, this router is in a confusion. Which path to choose? Should I go via router 2 or go via router 3 to reach 9.9.9.9? That's why next attribute comes into picture. It will check whether router 2 is having more weightage or router 3 is having more weightage. By default, the weightage for router 2 as well as router 3 will be 0. 0, 0. It's a Cisco proprietary attribute. By default, weightage will be 0. If the attribute is 0 on both the path, again there is a tie. It cannot decide how to go. So in case if your company policy says, if you want to go 9.9.9.9, go via AS2. Take the path via AS2. If that is your company policy, what you can do is, you can go to this router 1 and say router 2 is 10. Router 2's weightage is 10. So I give more weightage to whatever I learn from router 2. Router 2 is also advertising 9.9.9.9. Router 3 is also advertising 9.9.9.9. To whose advertisement I give more weightage? To router 2's advertisement I give more weightage because the weightage is 10. By default it is 0. So router 3 has got by default 0 weightage. Router 2 has got 10 weightage. Bigger the number, more preferred. So router 1 decides to send the packet, send the traffic destined to 9.9.9.9 like this. Like this. So this is what weight attribute. You can use the weight attribute if you want. According to your company policy, you can use weight attribute. Now, this weight attribute you will use only if you want to decide this in this router alone. See, in this router you may have many routers. In this autonomous system, you may have many routers. But you are not worried about all the routers. Only this router, one router, first router, needs to go via AS2, AS4 and AS5. Then you use weight as the attribute. Weight attribute if you set in this router, only in this router decision will be made like that. Not on the other routers in the autonomous system. The other routers in the autonomous system will take some other path according to some other attribute. We will discuss about that. Wherever there is a tie break, it will use that path. Now what we do is, because R1 wants to go always via AS2 to reach 9.9.9.9, we made R2 to have more weightage. By default, the weightage for every neighbor is 0. When I increment the weightage for router 2, whatever I learn from router 2, that is given more weightage, more preference. So if router 2 says, come to me, I'll take you to 9.9.9.9, then this router will obey that and send the traffic for 9.9.9.9 via router 2. So this is weightage, weight. And this you will see only on Cisco router. Weight. Next, let's come back to our default story. By default, what is weight? Weight is 0. By default, weightage is 0. So if weightage is 0 by default, then there is a tie. So it has to decide some other path based on what? That is what attribute number 2, which is local preference. Now local preference by default is 100. Local preference by default is 100. Bigger is preferred. Bigger is preferred, meaning, see, by default R1 has 100 as a local preference for router 2 and 100 as a local preference for router 3 and for all neighbors. If it has more neighbors, for all neighbors, the default local preference means, what is local preference? Locally preferred. Which locally? Is it local to the router? No. Local to the autonomous system. Local preference, scope of local preference is within this autonomous system. Say for example, if I go to router 1 and say, I give local preference 150 to router 3. Every router will change the local preferences 150 to router 3. So if you do changes on one router, that will be impacting all the routers. That will make the change on all the routers in that autonomous system only, within that autonomous system only. So all the router will change the local preference as 150 for router 3. But what is the default local preference? 100. So local preference is local to the autonomous system. Weight is local to the router. Weight is local to the router. When you change weight, it will change only on that router. Only that router will decide based on weight, not all routers. But if you change local preference on a router in an autonomous system, every router in that autonomous system will take that as the local preference for that particular neighbor. So local preference is preferred all over the autonomous system. Now, I made local preference as 150 to this neighbor and 100 to this neighbor. So what will happen? R2 is also advertising, R3 is also advertising, but R3 whatever advertises is given more preference and considered as the best route to reach 9.9.9.9. But one thing you need to understand here. Only if there is tie in this one and this one, it will come to this one. If there is no tie on the above one, if this is a tiebreaker, someone has set weight, then it won't come and check the next line local preference. It will not decide based on local preference. So we need to tune according to our attributes or according to our policies. Now, do I need to change the policy for the entire autonomous system or on a single router? if I want to implement the policy for the entire autonomous system, then I'll choose this as the attribute. I'll not touch weight. Weight by default 0, 0. It will not be considered a tie because there's a tie. And I'll make sure there is valid next hop. I'll not touch this. I'll just tune only local preference so that all router in the autonomous system will decide to go like this only to reach 9999, because that's what the policy says in my company. It won't take this path. If my company policy says for some reason only router 1 should go via router 3, other routers can go via router 2 or some other route, then only on this router I'll set wait, because that's for one router. So local preference is local to the autonomous system. Local to the autonomous system. Wait is local to the router within the autonomous system. So local preference is the third attribute from the beginning. 1, if you say this is 1, 2, 3. Local preference is the third attribute. Local preference. The next one is, this is the fourth attribute. If you start from 1. The next one is origin. Origin. I don't think there will be, okay, whatever. Origin means, from where it is originating. Locally originated is more preferred than originating from some other autonomous system. Example, see 9.9.9.9 is coming from autonomous system 5 to 3, 3 to 1. Let us say here also I have 9.9.9.9 advertised. There are two different places from where it is originating, and router 1 is learning from two different source. One from its own autonomous system locally originated, the other from some other autonomous system. Which one it will choose? It will choose the locally originated. Router 1 will not have route to reach this 9.9.9.9. It will have route to reach only this local 9.9.9.9. So this is another attribute. Right. Next is after local origin, what it does is it will look into this one, shortest AS path. Shortest AS path. Shortest AS path. Now, you see, when an update is given from R4 to R2 and R2 to R1 for 9.9.9.9, what will be the AS path? 2, 4, 5. See, 9 is originating from 5. 5 is giving to 4. 4 is giving to 2. And 2 is giving to 1. So on 1 you will find something like this. This is what called as AS path attribute. AS path attribute. This is via router 4. Via router 8, when the update comes to router 3 and router 1, this is how it will be. 8 and 9. Sorry, not 8 and 9. 3 and 5. AS5, AS3. So the last number is from where originates. So 9.9.9.9 is originating from 5 given to 3 and 3 is giving to me. Now which one I'll choose? If there is tie in all the above attribute, there is a tie in this, there is a tie in this, there is a tie in this, there is a tie in this. Now only it will come and check the shortest AS path. This is shortest, only 2 numbers, 2 AS in the middle, only 2 jumps, only 2 autonomous system. Whereas this one has got 3 autonomous system. So which is shortest? This is shortest. So what it will do? It will decide, you don't set any preference, any origin, nothing. Automatically it will decide to go via this way if you don't configure any attribute, because of less AS path, less autonomous system in the path. Now comes the policy. Company policy says no. By default it is going like this, but I want packet to go like this. Now you need to tune the local preference or wait depending on your need. If you want all the routers in this autonomous system to go via the upper path, choose local preference. If you want only one particular router in this autonomous system to choose the upper path, then use wait. So fourth one is shortest AS path. Shortest the AS number, lesser the AS autonomous systems in the path, more preferred. Okay, let's say there is a tie. Assume there is a tie. In our diagram there is no tie. This is a tiebreaker. This is the shortest path, so it will go like this. Assume there is another autonomous system here called AS6. Then you will get what? Tie. 3 numbers. 3, 6, 5, 2, 4, 5. 3 autonomous. There is a tie now. Now if there is a tie, it will go and check the next one. Next says I is preferred over E. I is preferred over E and E is preferred over question mark. What it means? Internal means don't think that it is talking about internal to this autonomous system. No. Internal means, see, this 9.9.9.9 here I use network command and advertised it. Mask, and then I wrote mask. Someone also here has got 9.9.9.9, but he is not using network command to advertise it. He is using redistribute command. Now when I use network command, it is BGP's own network. When I do redistribution, it is from some other protocol or some other static route. It is not BGP. That is what question mark means. Question mark means incomplete. Incomplete means what? It is not coming from BGP. Now let's say this one has got question mark because it is coming from, let's say, 7 here. Assume there is an autonomous system 7 which is redistributing 9.9.9.9 and this autonomous system 5 is using network command here. Yeah. So there are 2 different ways in which 9.9.9.9 is given to BGP. One by using internal command called internal network command. The other one is coming here because of redistribution. It is not by using network command. Somewhere from some other protocol it has been redistributed inside BGP. Which one need to be preferred? I is preferred, more preference. So this routers will go this 9.9.9, it will not go to this 9.9.9 because redistribution is done here. So redistribution is not preferred. Network command is preferred. So this is another example. Alright, so this is fifth one. There is one more, sixth one. What a sixth one says, I can set metric. Let's say here I say metric. Metric means this is not METRIC, this is MED. Mid value. MED. Mid. Multi-exit discriminator. Multi-exit discriminator. Mid. Lower is preferred. Lower is preferred. I'm sorry, it is not here. It is here. I configure mid on R4. Let's say I say mid is 5 and here MED is 0. By default MED is 0. I'm saying MED is 5. See, lower is preferred. So these routers will prefer to go via this way, not the top way. Now one thing very important here, MED is affecting the other autonomous system. I configured here, but it affects the path selection on the next autonomous system. Whatever you saw so far before this MED, all are affecting the same autonomous system where you configure. But MED is the one which affects the neighbor autonomous system. If this neighbor is configured with 5 here and here no configuration, this 5 path will not be selected because bigger is not really appreciated. Bigger the MED not preferred, lower the MED preferred. So these routers will prefer to choose the path with lower MED. So it will go via this way to reach 9.9.9.9, not via some other paths. Now these are the things that are under your control. Now we are going to see another 5 metrics. They are not under your control. These things you can change according to your company policy, and you can have some path selection according to the policy. The other 4 or 5 things that we are going to discuss now, they are automatic. You cannot do anything with it. Now before we go there, I want to say something to you. See, I'm just taking one example 9.9.9.9 and trying to explain all attribute. In the real world, there are hundreds and thousands of network coming from various directions. So it will be big, but the attributes are the same. So we will see, we'll see some example when we do the lab here. I'll also give you, I think I already given you this video, AS path videos. I want you to go through after this class once again, so that when I explain this, when I demonstrate this in the next class on Monday, you will be more comfortable. This is very important topic and final topic in BGP. So only if there is a tie in all the above, it comes to the 7th one. It is very rare that it will come to 7th one. Even in a very big network, there will be a tiebreaker before this itself. Now even if there is a tie after reaching MED, then what it will do, it will prefer the path via eBGP over IBGP. It prefers the path via eBGP over IBGP. Let's say this router 1 is directly connected to this way. There is no router 3. Assume there is no router 3. Router 1 is directly connected to router 8. So router 1 is learning the update from eBGP, which is router 8, and also from IBGP, that is router 2. Which one it will prefer? It will prefer to go via EBGP. Same network, learned from two different sources. One is IBGP, another one is EBGP. Which one it prefers? It prefers to go via EBGP than going via IBGP. Next, let's say you are learning from both are IBGPs, or you are learning from two EBGPs. So there is a tie now. If there is a tie in this, then it will see the lowest IGP cost. Very important. What does this IGP means? How much is the cost to reach this neighbor, and how much is the cost to reach this neighbor? IGP means what? Internal Gateway Protocol within this autonomous system. Within this autonomous system, I am learning from two different neighbors. Who has got lower metric? Let's say here between R1 and R2 cost is 100 OSPF you are running. Between 1 and 3 you are running OSPF again, cost is 50. Which IGP cost is lower? 50 is lower. No, it will prefer this one. Lowest IGP cost. It is not BGPs. It will see what is the cost that is provided by the local routing table. If I have routing table, if I have routing protocol, it will see the routing protocol's cost. If I have static route to reach these two, the metric will be the same. The metric will be the same. So there is a tie again. Then it goes to what, the ninth one. It goes and picks the one with the smallest router ID. Neighbor with the smallest router ID. Neighbor with the smallest router ID. I was telling you, for the last 2-3 classes that OSPF, like OSPF, BGP also will pick a router ID from loopback interface. Let's say this guy has got 2.2.2.2, this guy has got 3.3.3.3. It prefers the smallest router ID neighbor to reach that 9.9.9.9. Smallest neighbor with smallest router ID. There is very less chance for two routers to have router ID same. See, because your let's say I have one router connected here and here, and this router will see whether this router has lowest. This router means router 4 has lowest router ID or router 8 has lowest router ID. Let's assume accidentally both the routers are having same router ID. This is a very rare case. Assume. Only then it will go to the 10th one. What does the 10th one says? 10th one says pick the path with the smallest IP address. So neighbor's IP address should be smallest neighbor IP address. Neighbor's IP address should be smallest. That will be definitely there. If this is 24.0.0.4 and if this is 38.0.0.8, which is smaller, 24.0.0.4 is smaller than 38. So it will pick via this way. This cannot be same at all. So your attribute is over. Totally 0 to 10 attributes. If you start from 1, it is 11 attributes. It's not 0 to 11, it is 1 to 11. These are the BGP attributes. By using this, we can tune our path. If you don't tune your path, it will decide based on one of this automatically. If you don't tune local preference, it will do based on some other attributes. If you are not tuning based on weight, it will do according to some other attribute if there is a tie. Wherever the tie breaks, accordingly it will decide the path to go. So let's have a quick review. First, when it learns route from two different sources, it will check which one has got valid next hop and which one is not. It will pick the one with a valid next hop. If there is a tie in that one, only then it will go and check the next one. Which one has got highest weightage? By default, weight is 0 and it is a Cisco proprietary attribute. Will be seen only on the Cisco router as an attribute. The bigger the weight, more preference is given to that neighbor and it will go via that neighbor. By default it is 0 and weight is only to that local to that router. Next comes local preference. Local preference, this is also bigger is preferred. By default it is 100 with all the neighbor. When we tune the local preference, whichever the neighbor that has got a higher preference, local preference, that router will be selected as the best path. And this local preference is local to all the routers in the autonomous system. Local preference attribute will not be transited to the neighbor. It will not be given. There are some attributes which are transited. There are some are non-transitive, some are optional, some are optional non-transitive. These things are explained in the theory video which I have given you. But this is the main content. Those things are just theory. Now local preference is local to the autonomous system. It is not transited to the next autonomous system. Origin, from where it is originating. If there are two sources, one says locally origined, 9.9.9.9 is coming from the same autonomous system. That's what locally origined. 9.9.9.9 is coming from the other autonomous system. So there are two sources. Which one to believe? Local origin is preferred. That will be seen in the routing table. Now let's say all this above are tie, then it goes to the shortest AS path. When I am learning from two different sources to reach 9.9.9.9, which path has got less number of hops, less number of autonomous systems, that path is preferred. Even if there is a tie in this, internal networks are preferred than redistributed network. E is, you will not see E anymore. We don't have E. We have I and question mark. I is preferred than question mark. Once there was a protocol called EGP protocol. We don't have that protocol now. BGP was in two different flavors, EGP, BGP. Now we have only one, BGP. So if there is a tie even in this, then only it goes to MED. MED is a transitive attribute. Whatever you configure here is transited to the next autonomous system. So next autonomous system will decide whether to choose this path or this path based on the neighbors which has got lower MED. By default MED is 0. MED by default is 0. 0. Lower is preferred. If a path has got more MED, if this AS2 has got more MED, then it will not be considered as the best path by this AS1. AS1 will not decide to go by AS2 if MED is more on AS2. Even if there is tie, it will prefer the neighbor. If there are two neighbors giving the update, one is an eBGP neighbor, another one is an iBGP neighbor, it will prefer eBGP neighbor. If both are eBGP neighbors, then there is a tie. Or if both are iBGP neighbors, then there is a tie. So it prefers the lowest IGP cost. So within the autonomous system, you may be running OSPF. It will see what OSPF says. What is the cost for OSPF to reach that neighbor? It will choose the neighbor to which there is a lowest cost provided by IGP protocol. If there is a tie even in that, then it will choose the one with the smallest router ID, which is not at all really possible to have two different autonomous system neighbor having same router ID. But sometimes there are very rare case. Even if there is a tie in this, then it picks the path with the smallest neighbor IP address. definitely IP address cannot be same on two different autonomous systems. This is connecting to the public networks. In public, IP addresses are unique. So this comes as a tiebreaker. There is no other option. I'm sorry, I think this is the 11th one. Now I remember what comes here. Ninth is it prefers the earliest neighbor. I'm learning route from two different neighbor. Which neighbor came first to form neighborship? Which neighbor has formed neighbor with me? That neighbor I prefer. Only if there is a tie in this, I go to this one, and then it's correct. Then it is 0 to 11 attributes totally. And this thing you should know in order. Very, very important. After this, you may be working for 10 years or 8 years in networking. And then if you try to go to another company to get a job, this question will be asked even that time. After 10 years of experience also they will ask you this question. Very, very important topic. AS path. So I'll stop here. I prefer